Man, changed it in one place, but not the other. All right. Parameters and statistics. Okay. All right. A parameter is some characteristic of the population. In other words, what percent of this entire bin is red? Everybody with me? So it's worth noting that parameters are constants. They are not variables. Okay? There's only one percentage of this bin. Just because it's unknown doesn't mean it's a variable. It stays the same over and over and over again. Okay? Statistics describe that exact same characteristic of a sample. So it would like, for instance, the percent of the sample that is red. And you guys, statistics are a variable. They change depending on the sample. And so we're going to talk about, for the next few months, through February, we're going to talk about basically two types of statistics and parameters, okay? So one of the things that we have are different notations to talk about different statistics versus parameters. And we've already kind of talked about this a little bit, where we've used the symbol for the mean, we've used mu, and the symbol for the mean, we've used x bar. And really the idea is when we have the mean of a population, we use mu, and the mean of a sample, we use x bar. And that so it's going to start becoming incredibly important that you guys use the right symbol. And you might hear me stop using the word the mean. You might hear me start being more specific, like the population mean or the sample mean. Is everybody with me? The sample mean is a variable. The population mean is a constant. We don't know what it is, but it's a constant. Everybody good? What's the symbol for the parameter for standard deviation? We've used two different symbols for standard deviation this year, yes? One of them is the Greek letter sigma. It's when we're describing a population. S describes the standard deviation of a sample. So really, there's only one set of symbols that we don't know. Okay, when we're talking about the population proportion or percent, we use the letter P. Does anybody want to guess? What? For the sample? Yeah. Well, so we don't want to use P and P because we want to be able to tell, is this, like when we write this notation down, it's S? S is the standard deviation of a sample. It turns out it's very similar to P. It is a P with a hat. P hat. And that's how we would pronounce that. P hat, X bar. All right. Gallup poll asked a random sample of 515 U.S. adults whether or not they believe in ghosts. Of the respondents, 160 said yes. So, if I ask you guys what is the population in this study, you would say what? That is not the population. That is the sample. So if I have a random sample of 515 U.S. adults, my population would be U.S. adults. Wherever my sample was drawn from, yeah? Okay. And what is our, what are we trying to estimate here? So our parameter is going to be a P, and which is the proportion of U.S. adults who believe in ghosts. Our statistic would be our P hat. And if I asked you guys to calculate P hat would be the percent of the sample that believes in ghosts. What would that be? You would do 160 over 515. That would give you your P hat. Thoughts? What is 160 out of 515? So 31% is my P hat. All right. In a random sample of 318 teenagers, the mean screen time was 4.5 hours. Okay. So what's my population in this case? And my sample is the 318. What am I trying to estimate? It's not going to be a proportion. We're going to use mu in this case. We're going to describe mu as the population mean screen time. And the statistic is going to be X bar, which happens to equal 4.5 hours. For now, we're going to skip the samples of starbursts because I didn't realize I put these in here, and we should wait until I have starbursts for you guys to actually do this, but we'll do starbursts on Thursday. All right, but we'll come back to it, I promise. Oh boy. All right. So let's go ahead and say Mr. Bell takes a sample and estimates to try to estimate how much time people spent studying for midterms. And so he takes a sample of 10 kids and they answer with 6.2 hours on average. But Mr. Stork does a different sample, and for his sample it's 5.6 hours. Why aren't the samples the same? So X bar for Belk was 6.2 hours. X bar for Stork was 5.6 hours. Two different means because samples have variability. What's another way of saying samples have variability? Samples are not perfect. Have I made you guys repeat that with me yet?
Yes.
Enough times?
Yeah.
Are you sure? Well, I'm sure you guys are feeling that way. The FST kids from last year, we said it every day for like a semester at least. Yeah. So imagine Mr. Stork and Mr. Brown take every single possible sample of 10 students. So we could have, I'm going to maybe go from 3, 4, 5, 6, 7, and 8. So this is one of the X bars. That's Mr. Brown's sample, right? And Mr. Stork's sample is this one. And then Mr. Richards could take a different sample, and his sample's at 3.9. Okay, and then Mr. Hecker takes a different one, and his is at 7.5. Is everybody with me? And all of a sudden, I have a distribution of sample means. Okay, and if I take every possible sample, if it's every possible sample, we call that distribution a sampling distribution. And everything with sampling distributions, okay, everything with sampling distributions is how we do the rest of this 9 weeks and into next 9 weeks. Okay, that's what Unit 5 is all about, is sampling distributions. All right, so from here, I'm going to pause because we're going to go to... So as we think through what just happened, as n increased, the standard deviation of those X bars decreased. And why is that good? Well, I'm going to draw 2 graphs for you real quick. Which of these graphs makes it easier to estimate what the actual center is?
The first one.
The first one, and why? Because it's less spread out. Is everybody with me? Okay? Like, if I told you that both of these graphs came from the same population and asked you what is the mean of that population, you would say 2, yes? Except for when I say that 2, like this one, I'm trying to keep the scales about the same. For the top graph, if I only get to pick one of my means, all of them are really close to 2. For the bottom graph, if I only get to pick one of those samples, they're not all close to 2. Do you guys see what I'm saying here? So we want a low standard deviation because we're trying to guess what is the mean, and we want them to be close to that mean. Okay. So there's 2 reasons we really like a large sample size. The first is that the standard deviation decreases. And the easiest way of saying that is X bar will be closer to mu. or P hat will be closer to P. Both of those are what we want. We want our statistic to be close to the parameter, and that happens when I have a large sample size. Okay? The other thing is that as my shape increases, either the X bars or the P hats, they both get closer to normal. And normal distributions are super predictable and easy to work with. And that is where I'm going to stop today and let you guys work on corrections for the second half.